ControlNet is considered a legacy industrial automation network today. So you may wonder, why are we talking about ControlNet now? The reason is simple. Even though ControlNet is a legacy technology, it is still running in many factories and industrial plants. There are machines and production systems that have been operating reliably for many years using ControlNet. For maintenance and automation engineers working with these systems, understanding ControlNet is still very important. When a breakdown occurs, the maintenance team needs to understand the network architecture, communication mechanism, hardware components, and troubleshooting methods to identify and resolve ControlNet-related problems. But there is another important reason to understand ControlNet. Many industries are now looking at upgrading their legacy ControlNet systems to modern industrial EtherNet networks, such as EtherNet. And this is where our ControlNet to EtherNet migration series begins. When planning a network migration, we cannot simply remove the existing ControlNet network and replace it with EtherNet. A successful migration starts with understanding the existing system. We need to understand how the ControlNet network is structured, how devices communicate, what functionality the existing system provides, what its limitations are, and what needs to be retained or improved in the new EtherNet architecture. In fact, we have a ControlNet to EtherNet network upgrade project coming up very soon, and we will use this real-world project as a foundation for this migration series. In this series, we will go beyond simply explaining ControlNet. We will first understand the existing ControlNet system, its architecture, communication mechanism, hardware, scheduled and unscheduled communication, NUT, network update time, and the characteristics that made ControlNet suitable for industrial control applications. So whether you are a maintenance engineer, automation engineer, PLC programmer, system integrator, or someone working with legacy automation systems, this series will help you understand not only how ControlNet works, but also how to approach its migration to EtherNet in a practical and structured way. This is the ControlNet to EtherNet migration series. Understand the existing, design the future, execute the migration. So let's get started. Why ControlNet was attractive for industrial automation? Deterministic communication. ControlNet guarantees that critical data gets delivered at a fixed, predictable time every single network cycle. It does this by dividing time into repeating slots called the network update time and reserving part of that window purely for scheduled priority traffic like I/O. Nothing else is allowed to interrupt that slot. Scheduled communication. Every device on a ControlNet network is pre-configured using the network configuration tool with its own reserved time slot inside each network cycle. Instead of devices contending for the wire like on older Ethernet, each node already knows exactly when its turn is, so critical I/O data go out like clockwork, cycle after cycle. Anything less urgent, like uploading a program or a one-off message, gets pushed into the unscheduled portion of that same cycle, so it never competes with or delays the priority traffic. Predictable network update time. ControlNet's entire cycle, called the network update time, NUT, repeats at a fixed engineer configurable interval, typically around 5 milliseconds, adjustable roughly between 2 and 100 milliseconds, depending on the network's needs. Because that interval never drifts once it's set, engineers can calculate exactly how often a piece of I/O data will refresh and design their control loops and interlocks around that known number, not an estimate. Passive bus, the ControlNet trunk cable itself is just plain coax with simple unpowered taps connecting each device. There's no active switch or powered hub in the middle doing the work, the way there is on a typical Ethernet network. That matters because a passive tap has nothing in it to fail. Supports hot redundancy. ControlNet could run on a fully redundant dual coax cable setup. If one cable was cut, damaged, or lost power, the network switched over to the second cable instantly with no drop data and no interruption to the control system. That was a big deal because within the Rockwell/CIP ecosystem, ControlNet's built-in cable redundancy was the go-to option for critical always-on applications until Ethernet/IP's device-level ring DLR came along and finally brought that same seamless, bumpless failover to EtherNet. ControlNet is built around a coax trunk cable. that PLCs, I/O chassis, drives, and HMIs tap into using simple passive taps forming a bus. You can extend it with repeaters or fiber for distance, branch it into a star with a hub, and even run a second redundant cable in parallel so one fault never takes a network down. Wherever a device sits, it shares the same fixed network update time, so every node still gets its guaranteed scheduled turn to talk. The trunk is the main coax backbone running through the plant. Quad shield RJ6 cable that carries all the network traffic from end to end, up to 1000 meters without repeaters. Each device doesn't connect straight into that main line. Instead, it connects through a short drop cable and a passive BNC tap branching off the trunk at that point. Keeping drops short and using proper taps is what preserves the signal quality along the whole bus. It's the same trunk and drop pattern you would see in old cable TV wiring, just repurposed for deterministic industrial data. A node is simply any device on the network with its own unique address, a number from 1 to 99, usually set right on the device with rotary switches or thumb wheels. That address is how the network keeps every device's scheduled time slot straight. So the PLC, I/O adapters, drives, and HMIs all know exactly whose turn it is to transmit. A single ControlNet segment supports up to 99 such nodes, which is generally plenty for a plant floor cell or process area. Bigger installations just split into multiple segments linked together. ControlNet runs on RG6 quad shield coax. The extra shielding layer matters since standard RG6 isn't rated for the electrical noise you get on a factory floor. Devices and taps connect using BNC connectors, the same twist and lock style you'd recognize from old video and antenna cabling, chosen because they're quick to install and give a solid, reliable connection on a vibrating machine or panel. For longer runs, tougher environments, or electrically noisy areas, ControlNet can also switch over to fiber optic cable instead of coax. Every ControlNet trunk cable needs a 75 ohm terminating resistor installed at each physical end of the line. Coax works like a signal highway. When that signal reaches the end of the cable and there's nothing to absorb it, it reflects back down the line, colliding with new signals and corrupting data. The terminator matches the cable's impedance and soaks up that energy instead of bouncing it back, keeping the bus clean. It's a small passive component, but skip it or leave a segment unterminated during installation or troubleshooting, and you will get unreliable communication or nodes dropping off the network, even though everything looks physically fine. Every ControlNet cycle, the network update time, is split into two parts. The scheduled portion is reserved, guaranteed bandwidth. Each node gets its own pre-configured time slot to send its critical I/O and interlocking data, and that slot happens every single cycle without fail. The unscheduled portion is more like EtherNet's old approach. Nodes take turns passing a token, sending things like program uploads, MSG instructions, or configuration traffic on a best effort basis whenever there's room left in that cycle. The split means the two never compete. Your time-critical control data always gets through on schedule, while everything else just fills in the leftover bandwidth. NUT is the name for ControlNet's repeating cycle, the fixed window of time, typically around 5 milliseconds, that repeats continuously as long as the network is running. Each NUT is broken into three parts. First, the scheduled phase, where every configured node sends its guaranteed priority data in its own reserved slot. Then, the unscheduled phase, where nodes take turns passing a token to send lower priority traffic like messaging or programming. And finally, a short guard band, a quiet maintenance window that lets new nodes join and resets the cycle cleanly before the next NUT begins. That whole sequence, scheduled, unscheduled, guard band, repeats over and over, which is what gives ControlNet its predictable clockwork timing, bandwidth. ControlNet's trunk cable is a single shared bus. Every device is physically on the same wire. So without some kind of traffic control, multiple nodes could try to talk at once and collide, exactly like early contention-based EtherNet. So every node's transmission time had to be pre-planned and reserved in advance, eliminating collisions on the scheduled portion entirely and guaranteeing that critical data always arrived exactly when expected. Rockwell has moved ControlNet products from active to active mature status and now recommends EtherNet for all new installations. So most plans running ControlNet today are looking at this as a when, not an if. The jump is significant. EtherNet/IP offers 20 to 200 times the bandwidth, room for 254 nodes instead of 99, built-in CIP security and CIP safety that ControlNet never had, and device-level ring redundancy that finally matches ControlNet's old advantage of seamless cable failover. So that brings us to the end of this episode on ControlNet. We have looked at why ControlNet was developed, how its architecture works, how scheduled communication and NUT provide deterministic performance, and why ControlNet is still found in many industrial plants today. We also discussed why industries are now moving from ControlNet to modern industrial Ethernet networks such as EtherNet/IP. But understanding the theory is only the first step. In the next episode, we are going to take this one step further. We will be working on a real ControlNet to Ethernet/IP migration project, and I will walk you through the actual engineering approach, understanding the existing ControlNet architecture, identifying the hardware and communication requirements, designing the new Ethernet/IP architecture, and planning the migration. This will be a practical, real-world migration project, not just a theoretical discussion. So if you are a maintenance engineer, automation engineer, PLC programmer, or system integrator, and you are interested in understanding how a legacy industrial network can be upgraded to a modern Ethernet architecture, make sure you follow this series. ControlNet was built for the past. Ethernet IP is shaping the future. And in the next episode, we start the real migration. See you in the next episode.